Welcome, everyone. For today's prep, I want to look at one more example where we calculate the derivative of a function using that limit definition. So we're going to look at the square root of x. We're going to calculate the derivative. So let's start by writing down the formula, the limit definition formula for derivative. So we'll call our derivative f prime of x, and it's the limit as h goes to 0. And then we have that difference quotient, that big fraction, f of x plus h minus f of x all over h. All right, so it's always good practice. Just write down that formula. Okay, so now the next step is we want to work with this f of x plus h. So if we look at our formula, wherever I see an x, I'm going to switch that x to x plus h. So let's start with the first. It's kind of like the trickiest part, I think, my opinion. So we're going to have square root sign. So what we're doing here is we're plugging x plus h into this function. So we're going to have our square root sign, and then underneath will be the x plus h term that we're plugging in. All right, so that's f of x plus h. Then we're subtracting, and now we write just the original function right next door. So the original function is just square root x. So we're going to have just square root x there. And then all over h. So we're dividing by h there. All right, so we have our difference quotient all set up. Now, the issue that we've seen with these is this is always going to be that indeterminate 0 over 0 form. So, we have this set up. First thing we would normally try is direct evaluation, but direct evaluation wouldn't work here. It would be just 0 over 0. So we have to do some algebra to kind of simplify or kind of change this difference quotient. And one of our strategies that we looked at before when we looked at those 0 over 0 forms, when we have square root terms and we're either adding or subtracting, we can kind of rationalize the numerator. So we use the conjugate here. So our algebraic trick would be to multiply by the conjugate. So it's the exact same thing. The only difference is we have a minus sign here, so we're going to change it to a plus sign. And we can't do something to the numerator without doing the same thing to the denominator. All right, so this was our conjugate method. So if you need to go back to our 0 over 0 notes to see this in action. All right, so we have our conjugate there. Now we want to multiply it through. So we take the numerator and we multiply it with this numerator. And the nice thing with the conjugate method is when we do it, really, we just square this term, we square this term, and then the minus sign just kind of stays in the middle. So you can work out multiplying it out, but that's kind of the end result. We square this term, and then the minus sign stays in the middle. So if we write that out, we're going to have still the limit sign. H is still going to 0. And in the numerator, we're going to have x plus h minus x. So when we square the square root of x plus h, we just get regular x plus h. And when we do the square root of x, or we square the square root of x, we just get x. And then the minus is still in the middle. And then in the denominator, we have our h, and let's not distribute or anything. So we're just going to leave, we don't normally do too much with the denominator. So we're just going to leave it like that. And then if we simplify, a little bit of canceling happens in the numerator. We have x and then minus x. So those are going to cancel. And what we have left, we're still doing our limit, and then we have just h over h times the square root of x plus h plus the square root of x. And now we can see, kind of hidden in there, we're able to cancel out that h over h that was giving us the 0 over 0 form. So what we have left then is 1 over square root x plus h plus square root x. And once we cancel out that h over h, the very next thing should be to just do the direct evaluation. So now we can plug in h equals 0. And when we do that, we get square root x plus 0 plus square root x, which simplifies into, well, this is just square root x. This is just square root x. And we have two copies that we're adding together, so we just end up with 2 times square root x in the denominator. All right, so this was our direct evaluation step with h equals 0. So notice that when we did this direct evaluation step, h is the thing that's changing. H is getting smaller and smaller. It's going to 0. So when we plug in, we're plugging 0 in wherever we saw an h there. So the x's stick around. Okay. Also, just a comment about the limit notation. So this is something that we do, excuse me, we do look for. So each step should have a limit sign in front of it until we do that direct evaluation. And limit sign, remember, it's like telling us that we're kind of moving around. We're moving h around. So you want to think of limits as kind of like movement. And once we do the direct evaluation, that's when we've reached our destination. So correct limit notation would look like this. There's a limit sign in front of each of these difference quotients. And then once we do the direct evaluation, then we're good. Then no more limit sign. Okay. So we have the derivative of square root x. So I want to jump to the next section here and look at the definition and start looking at the definition of what does it really mean for a function to be differentiable. And we'll see some different interpretations of this. So differentiability, as we've seen, a function f is differentiable at x provided this limit exists. So this limit that we've been practicing and calculating with. So if this limit, for whatever reason, 0 over 0 form, you can run into issues. So if that limit does not exist for whatever reason, well, then our function is said to be non-differentiable at x. So we're going to be, investigating this idea of what does it mean to be non-differentiable? What can happen if this limit gives us issues? So with that, we want to think of the derivative as just a brand new function. So f prime is the name of this brand new function, and it's derived from the original function f. And generally when we calculate these derivatives, if x is the variable of the original function, well, then we're also going to be using x for our variable in f prime. And then our original function has a domain, and it makes sense then to consider what is the domain of this new function f prime. Well, the domain of f prime is going to be all the x values from the domain of f, the original function, where this limit exists. So let's look at the function we were just working with, square root x. So we have the kind of the original. This is our original function. And we went through that whole differentiation process, and we ended up with its derivative. So this is what we just did. So our original function was square root x. We went through and calculated that limit, and we found that its derivative, f prime of x, was 1 over 2 times square root x. Okay. So what is the domain of square root? What is the domain of the original function? Well, square root x, for square roots, we can't have negatives under the square root. 0 is okay, and positives are okay. So the domain here is just whenever x is bigger than or equal to 0. So we could indicate that with an interval. It's the closed interval, so we use a closed bracket here to indicate that 0 is okay, and then it's all the positive numbers from there. Okay, so that's the domain of the original function. So when we go to when we calculate its derivative, at best, this is the domain. This could be the domain of f prime. So f prime kind of inherits all of these x values, but we have to look for any x values here that might cause some additional trouble. And in this case, there's one x value that causes us trouble. So if we look at this formula here, when x is equal to 0, we end up with division by 0. So the domain for this function, we have to throw 0 out. So it inherits most of these, but there is that one place that causes us trouble. So our original function had this closed interval 0 to infinity, and now its derivative kind of lost a little bit. So there's one point, this x equals 0, where it wasn't differentiable. So it's non-differentiable. At x equals 0. And let's kind of graphically look at what's going on. So we have, this is the original function, f. So this is square root x. And here is its derivative. So this is 1 over 2 square root x. And so what we see is that right at x equals 0, the slope is getting, remember we want to think of f prime as the slope of our function. What's happening right at x equals 0 is the slope of our curve is getting steep, is very steep. And actually what we have here, we have a vertical tangent at x equals 0. So if we were to draw our tangent line there, the graph is almost kind of vertical there. Now, if we look at the kind of the corresponding behavior in f prime, we can see that it has a vertical asymptote at x equals 0. So it's kind of going off to infinity. So f, the original function, has a vertical tangent line at x equals 0, and graphically what we're seeing here is that its derivative, f prime, has a vertical asymptote at x equals 0. So the graph is going up and up and up. Let's go back, though, to our limit calculation. So let's go see where in our limit calculation would we run into trouble with this x being equal to 0. Let's go back up. So here's all our work. Where would we run into trouble if x was equal to 0? Well, really, it would be if x was equal to 0, let's look at this step. Let's go back. So let's put a little asterisk here. And let's do this off to the side. So we kind of didn't really consider the x value here, but let's just see, for the fun of it, what would happen if x was 0 at this step. So if x was 0, we would have the limit h going to 0 So what happens if x is equal to 0? So this step would become the limit of 1 over square root 0 plus h plus square root 0. And this is then the limit as h goes to 0 of 1 over square root h. And this is a c over 0 form. So we know how to handle c over 0 forms because, well, first we could check that it's a c over 0 form. So the numerator is just approaching a constant, and then our denominator is approaching 0. So this is a c over 0 form. And we know c over 0 forms either are plus infinity or minus infinity. And so we could use a test number then, and we could see that, well, actually don't even really need a test number. Square root terms are always positive. So this fraction is always going to be positive, so we'd be approaching positive infinity. So, this is something not necessarily to always be actively looking for when you're calculating these limits. But when you get the formula for the derivative, you just want to think about, well, what was the domain of the original function? And in this new formula, does this introduce any kind of new issues? So our original function, 0 was perfectly fine, but when we went through the derivative process, the new formula here kind of gives us an issue now at x equals 0. So something's happening there. So we'll look at this a little bit more in class, and we'll kind of take this more graphical approach just to think about differentiability in terms of graphs. So we'll see you then. Bye-bye.